In the first part of this video lecture, we discussed how numbers and functions can be decomposed into a positive and negative part. We used this decomposition and the previous definition of integrals of non-negative extended Borel functions to give a general definition of extended Borel functions. We saw that this integral can sometimes be undefined, and it will declare the integral to be undefined only when we get infinity and minus, and both for its negative and positive parts. And we defined what it means for a function to be integrable. That is when both these integrals are finite. In the second part of this video lecture, we stated a theorem which gives the main and fundamental building properties of the Lebesgue integral for extended Borel functions. Then we stated 5 exercises that give us the properties, all the properties that follow from the axiomatic definition plus the definition given in terms of splitting positive and negative part. And now in the third part of this video lecture, we'll discuss the relationship between Lebesgue integral and expectation. And finally, after all the suspense we had from week 1, when we questioned our previous knowledge and our previous notion of what the expectation is, here we are finally ready to give a precise and unifying definition of expectation without formulas on how to compute it, but a conceptual definition, the mathematical definition of what the expectation is. And, ta-da, the expectation is nothing but the Lebesgue integral of a random variable on the probability space. We know that probability spaces are just particular cases, is just a particular case of a measure space. If the measure of the entire sample space is 1, we call it a probability space. And we know that a random variable is nothing but a measurable function from that probability space seen as a measure space. And a random variable is, technically speaking, nothing but a function from the sample space to the real line. And an extended random variable is when we allow this value to be plus infinity or minus infinity. And definition, very simple definition of the expectation of x is nothing but its integral on that space. And you see that this definition, it is in agreement with everything we want to say about what the expectation is, what it means, how to compute it, etc. To reconcile the definition of expectation, the proper definition of expectation that we just gave with our previous notion of expectation, here a few exercises to practice our understanding of Lebesgue integral in the case when the measure of the entire sample space is 1. Well, if a random variable only takes values between a and b, then its expectation is between a and b, and you are asked to prove this. Use only the fact that the expectation is the Lebesgue integral, that the measure of the entire sample space equals 1, because whenever we say random variable, it's implicit that there is an underlying probability space where this random variable is defined, and use the fact that the measure of the entire space is 1, together with the previous properties we have seen of Lebesgue integral measure spaces. Another very interesting exercise is if we take a random variable and we subtract from that random variable a number, so we get a new random variable, which is given by simply by shifting up or down the original random variable, then this new random variable, its expectation is 0. So assuming it is integrable, of course, because then we know the expectation is just a number. It cannot be plus infinity, it cannot be minus infinity. So whatever the value of x is, we can always subtract a finite number from it. This will still give us an extended real number. This is well defined. So this, assuming x is integrable, we have this interesting exercise that is also very helpful for us to practice our understanding of random variables, expectation, and Lebesgue integral. And this third part of this video lecture concludes the video lecture.